astronomers observe a black hole in another galaxy, tearing a star apart. During the 1950s, the study of the cosmos was revolutionized with the introduction of radio astronomy. In the ensuing decades, astronomers detected numerous bright radio sources that they designated as quasi-stellar objects, ACA, quasars. Along with the raio-bright region at the center of the Milky Way, Sagittarius A, these radio sources were revealed to be the core regions of galaxies with supermassive black holes, SMBHs. As objects fall in around these behemoths, they are torn apart by tidal forces. These are what is known as disruption events, TDEs, which release tremendous amounts of radiation in multiple wavelengths. Thanks to advances in instrument technology, astronomers have witnessed several TDEs that produced bright radio emissions, but all were detected within the core regions of galaxies. In a recent study, an international team of astronomers led by researchers from the University of California, Berkeley, UC Berkeley, reported the discovery of a TDE, AT2024 TVD, in a galaxy located 600 million light-years away. Unlike all previous events observed, this TDE occurred approximately 2,600 light-years from the center of its galaxy and is the fastest evolving radio emission of its kind ever observed. The team was led by Dr. Idai Esfarati and Prof. Rafla Margutti of UC Berkeley, and the Berkeley Center for Multi-Messenger Research on Astrophysical Transients and Outreach, Multi-Raptor. They were joined by researchers from the Raqqa Institute of Physics at the Hebrew University of Jerusalem, the Astrophysics Research Center, ARC, of the Open University of Israel, the Center of Interdisciplinary Exploration and Research in Astronomy, CIRA, the International Center for Radio Astronomy Research, ICRAR, the SETI Institute, the Berkeley SETI Research Center, the Leiden Observatory, and Breakthrough Listen. Tidal disruption events of this kind, a black hole-driven stellar disruption, are caused when stars fall in around black holes and are torn apart by their intense gravity. As the star circles the outer edge of the black hole, material is pulled from the surface and becomes a mess of ribbons, a process known as spaghettification. Such events have been observed around SMBHs, such as the Milky Way's own Sagittarius A. But in this unprecedented case, the roaming black hole and TDE took place roughly 2,600 light-years from the center of its galaxy, demonstrating that SMBHs can exist beyond galactic core regions. These observations were made possible by combining data from some of the world's most advanced radio telescopes. This included the Very Large Array, VLA, in New Mexico, the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, the Allen Telescope Array, ATA, in Southern California, the Submillimeter Array, SMA, in Hawaii, and the Arc-Minute Microkelvin Imager Large Array, AMILA, in the UK. The AMI observations were led by Prof. Asaf Horsch and his team from the Raqqa Institute of Physics. These proved to be of vital importance since they revealed the rapid evolution of the radio emissions, which offered clues regarding the physical nature of the radio bursts. In particular, the data showed two distinct radio emissions, a double-peaked event, evolving faster than any previously observed TDE. Meanwhile, computer modeling indicated at least two separate ejection events that occurred months apart. These powerful outflows of material occurred months after the star was consumed, rather than immediately after. As Esfarati said in a Hebrew University of Jerusalem press release, these results suggest that there are delayed and complex processes at work in the aftermath of disruption events, and that black holes can periodically become active again after periods of inactivity. Dr. Esfarati is a former graduate student of Prof. Asaf Horsch, a professor of physics at the Raqqa Institute who is also co-author on the paper. As he summarized,